Hi everybody, we are starting. How to develop new ensembles, right? So we already know what is a microcanonical ensemble is. Okay, we studied canonical ensemble. Right? Now, the question is, how or is there a way in general to develop any ensemble that you like? Okay? Now, microcanonical ensemble was built on the assumption that all the states are exactly equivalent, right? So all the probabilities to be in a specific state was simply uniform. We started from this assumption saying what is the least complicated distribution, which is of course is uniform. For canonical ensemble, what we have done, we in some sense continued with this uniform distribution, but we basically conditioned on the behavior of a heat bath, right? We introduced this heat bath around our system and we basically said, well, there is a concept of temperature which should be exactly the same in our system and in the heat bath, right? Now, the thing that was most important in the transition between the canonical ensemble and microcanonical ensemble, that we eased one specific condition. We threw out of the window that the energy of the system is constant. Everything became much more simpler when the energy is only on average kept constant, right? This is the equilibrium. We said, well, the total energy of the heat bath in our system is exactly constant all the time. But what we have assumed is that, well, our system, small system, in this huge, tremendous heat bath, is not conserving energy. It can exchange energy with the outside world, and only on average, this energy was constant. Now, we're going to use this concept of throwing away some specific conditions, right? Instead of saying, well, this specific quantity is constant all the time, which complicates everything because we have to use this constant value for everything that we perform. Remember, we had specifically construct the energy that it will be equal to the total energy. That was difficult, combinatorial problem. The moment we said, well, energy is not constant, everything became much more simpler. And this is what we're going to use. We're going to assume that some of the concepts or quantities that beforehand were constant, now they are going to be only constant on average. Okay? We will see how it's done today. In order to perform this, we need to actually define what this entropy and measure of disorder is. So we already seen what entropy for two different systems. So in the microcanonical ensemble, the entropy was S, it's K Boltzmann, log of the number of states for this specific system. This was the entropy. What happens in the canonical ensemble? So in the canonical ensemble is slightly different, right? How is slightly different? Well, we remember that F E U minus Ts. So S is basically U 1 over T U minus F divided by T, okay, those two quantities. And then we can introduce here this knowledge of number of states or probabilities. Okay. Now, what is F? F is minus 1 over beta log of Z. Z is our partition function. You can write it down as minus K Boltzmann T log of a sum over J, right? And here we have e to the power minus e to the power of minus ej, or sorry, minus beta ej, right? So this is the free energy. Now, explicitly, we already have a connection between the free energy, okay, and some specific probabilities. Because remember, the probability of being in state J is simply e to the power minus beta Ej divided by Z. Okay? So the moment that we have this expression inside of F, and in a couple of minutes, we're going to put it inside this entropy, we know that the entropy starts to be somehow dependent or related to the different probabilities of occupying different states in our system. So this is F. We can use this guy over here. U, what is U? Yeah. So U is the average energy, which is a sum over J, Ej, e to the power minus beta Ej divided by Z. So this is the average energy. Now, so we have the average energy, we have the free energy, the temperature we know. Okay. So what we are going to have inside, so S is what? S is K, it's 1 over T, right? Sum over J, Ej, e to the power minus beta Ej, divided by Z, okay, minus, okay, so this guy, minus or plus K Boltzmann T, log of Z. Okay. So this is one definition of the entropy, which is applicable to what? To canonical ensemble. This is the second definition of the energy, which is applicable to what? To microcanonical ensemble. Right? And they are completely different. They are very different, right? So here we're looking on some general number of states. Here there are probabilities, because this guy over here is Fj, right? So here we have different probabilities of being in a state multiplied by the different values of energies for each state, and also we have log of the partition function. So it's very different. Now, this is a little bit of peculiar, right? So because I want a general definition for the entropy, and it seems that I cannot simply use, well, K Boltzmann multiplied by log of the number of states. This is how we started, right? And then we waved our hands around and say, yeah, this is applicable because it's a multiplicative value and it looks like the entropy, but all right. So if this was the true definition of the entropy, it should be exactly applicable also to the canonical ensemble, okay? But we're not getting anywhere near this log of number of states. We have probabilities of different states, we have energies of different states, we have this partition function, etc., etc., etc. So it's very different, right? So we need to define something that is entropy, okay? A general measure of entropy, which is related to what we call measure of disorder, that will be applicable for the microcanonical ensemble and the canonical ensemble. Okay? And this idea, today we follow something that is started by Claude Shannon in 1940. Claude Shannon was an electrical engineer, and the measure of entropy, or the definition of entropy that we use nowadays, is basically follows his description of what is the measure of disorder. Okay, so we follow a definition by Claude Shannon, 1940. So what is measure of disorder? This measure of disorder over here. That's what part of the things that was in the focus of Claude Shannon, who basically is the father of modern information theory, how I define disorder. So if I have a system where I will look on my office, it looks very disordered, right? So everything is misplaced, I have a lot of balagan on my desk, different papers over here, different papers over there, computer, the laptop is in one place, the whatever is in the other. It looks very disordered how we define disorder today, or how my mother will like to define disorder, okay? But I can say no, it is a very ordered system, okay? Because, and this is what Claude Shannon tells us, order is not something that looks to us as misplaced, but order is the amount of permissible states. Okay? Permissible states. What I mean is, for example, if this marker is located over here, or those three markers are located on my desk over here, it looks like they are ordered in a specific line, and I will say it's a very ordered system. But if I'm telling you, well, this is not what's important. This is important if how can I misplace all the different markers on top of my table, of my desk? If the order or in which they appear, blue, red, or black, it doesn't matter. It introduces a disorder into my system. So the number of permissible states, of permissible ways that I can interchange all the different markers, this is disorder. Okay? That they are simply thrown on my desk and it looks like, well, you threw it out, it's disorder. No, it's not, because if I clearly state that this marker should be exactly over here, this marker should be exactly over there, and the black marker should be exactly in this exact position, then it's not disorder. There is only one exactly permissible state. If anybody will come here and touch it and say, I will say, oh, no, I have OECD. You have to return it exactly to this state, right? The system is ordered. Right? It's not about how it appears to us. It's about how many different states, okay, related to what we had for microeconomic example, there is in the system. Okay? The only thing is how exactly I count those states. Okay? So Claude Shannon said to us, well, the only thing that I care when I'm looking on the measure disorder, I have to define it by, I need the number of states that I have inside my system, and also I need to define the disorder by the means of FJs, right? The different probabilities to find the system in different states, in various states. Okay? Yes?
But you have to define the exact order in order to say what is disorder or
exactly.
order.
You're absolutely right.
You have to define it.
Exactly. You're absolutely right. You have to define what I mean order, what I mean disorder. Okay? And this is Claude Shannon. So although he was an engineer, he was a good engineer, right? So he went and defined mathematically, because information theory, it's a lot of math. It's basically math. Okay? He defined mathematically what disorder is. Okay? As you say, you have to define it because there can be several definitions, right? Okay. My mother definition for disorder is very different than mine. Okay? And we have to properly define it. And this is what Claude Shannon did in order to the requirements for definition of any disorder. Okay? You will see in a second. I do not say what is order, I just say what is disorder. Mm-hmm. All right? And the lack of disorder is order. Okay, so Claude Shannon requirements for disorder. Okay. So A, measure of disorder has to be defined entirely in terms of Fj. Okay. So the only thing that matters are the different probabilities. Okay. I can have many states of the system. The only thing that matters are all the different Fjs. I have to use the fj's and only fj's in order to define disorder of my system. B, if any of the fj's is 1, then the disorder is 0. What it means that if there is only one single state, what it means that fj is 1. So there is a specific state that the probability of having this state is exactly 1. This means that the system has to be in a very specific state, okay? Then the disorder has to be 0. Again, because the idea of Shen of what is disorder and what is entropy is how many different configurations can I obtain. Right? So if there is only one configuration, my disorder is simply 0. C, maximal disorder corresponds to fj equals 1 over omega. So basically, the uniform spreading, I can be in any of the states in my system. Right? I can be in any of the states in my system. This is maximal disorder. The Hashem. So basically what we say, microcanonical ensemble corresponds to maximal disorder that is present in my system.
אז זה לא בהכרח מספר המצבים, זה פשוט... יש לך מספר שם.
So the question is, what is omega? Omega is the number of states.
השאלה שלי אם זה בדיוק צריך... כשאני אומר יסר, אני מתכוון בדיוק למספר המצבים שיש לי?
No, we still haven't defined what is disorder. We still haven't decided what is disorder. We only know that maximal disorder corresponds to this state. This is part of the oxyons. We haven't defined what disorder is. Okay. See, look, here the number of states in the system can be very, very large. But if the probabilities are such that there is only one of the fj's equals 1, then disorder has to be 0. No matter how many different states my system has. Why? Because there is only one state that I can actually occupy. A, B, C, D. Maximal disorder is an increasing or disorder increasing, no, it's maximal, is an increasing function of omega. Two disorders of two systems construct linearly the disorder of a combined system. What I mean by that? So if G1, the probability to occupy, to be in system number 1, and G2 is the probability to be in system number 2. So disorder of combined system equals G1 D1 plus G2 D2. So this is the linearity combination. If I have two systems and I construct a new system out of this, then I can, based on the that on the fact that I know the disorder of the first system and I know the disorder of the second system, I can compute the disorder of the third system. I only need to know the probabilities of being on the first system or being in the second system.
It's multiplication. It's a function.
Okay. So now I know what it has to be in a very specific case. I know that it's completely defined by fj. I know what the maximal disorder is. The maximal possible disorder is. I know that in my system, the system is going to be spread maximally around its value based on all the constraints that I have inside. And I know how to go from two systems to a combined system. Okay, so based on all of this, the measure of disorder by Claude Shannon is very simple. Okay, so based on all of these axioms, I said the measure of disorder, D, equals to minus the sum over all the different states that I have in my system, fj log of j. Okay. So this is the measurement of disorder that Shannon introduced to us. And the disorder, which is how exactly the system is spread around all the different systems, right? The disorder is exactly the entropy that we use to basically not define by use very constructively during this whole class. We haven't defined exactly what entropy is, unless only in the micro-canonical ensemble. We had no idea what it is, right? It was something that is an extensive function and the energy is growing as a function of energy, and we had this second law of maximal entropy, etc., etc., etc. But we had no definition of what entropy is. So this is the first time that we actually define entropy. But this is a unitless value, right? So in order to be okay with all the different units, we have to introduce here some constant, and this constant is k volt. So now we have an exact introduction, a definition, of the entropy, any kind of entropy that we have in our system. And this entropy, as we will see in a second, right, it is what we found for the microcanonical ensemble, and it's also what we found for the canonical ensemble. Right?
Stas,
Yeah.
isn't this like information theory?
It exactly information theory. Who was Claude Shannon? He's the father of information theory. This is information. This is what he means by information. Okay, we call it disorder. It doesn't matter. But it's exactly the same thing. Information is how this something, distribution, is spread around your whole system. We're talking about how the probabilities are spreading around your system. Okay? This is exactly information. There is a very strict connection between statistical mechanics and information theory. Yes.
Why the disorder goes by minus?
Because all of the fj's are between 0 and 1. So log of something between 0 and 1 is minus.
Yeah.
This is why you need to have minus and stuff. Right? Because he introduced the log over here. Right? It has to be, you're completely right, it has to be positive function.
Yeah.
Right? So the minus is because this function is negative.
Cancels the minus.
Yeah.
About the combined system,
Yes.
if we combine two systems, we say that the interaction between them doesn't add new states.
You remember, so for large enough systems, yes. Yes. When you remember when I defined entropy, or I spoke about entropy, I said that it's an extensive property. This is exactly what it is. Okay? This is exactly what it is. Now, all of these definitions sometimes have to be a little bit different when the interaction is very long range. We won't mention such systems in our class.
יש לי שאלה סטאס.
Yes.
כשאתה אומר בעצם ההסתברות להיות במערכת אחת, של מי ההסתברות הזו? ההסתברות של כל
The
המערכת?
total system. It can be over here, over there. You will see it. You will see it soon enough.
אוקיי,
All right.
G1 כפול D1 זה בעצם האורדר של מערכת אחת, נכון?
The disorder of one system is D1.
אוקיי.
And disorder of the second system is D2.
Yeah,
Okay? And G1 are the probabilities to be. If you have a combined system, it's either here or either there.
כן, וזה לא C, זה E.
Where?
C רשמת D, C רשמת כבר C.
אז
זה
אפשר.
E פשוט.
A, B, C, E, E. Okay, thanks. Okay, so what happens in the microcanonical ensemble? Microcanonical ensemble. So we do know that what is Fj? 1 over omega. Okay, so let's see what the disorder is. Is minus K Boltzmann sum over J, J, 1 over omega, log of what? 1 over omega. Okay, so we said that the simply minus K Boltzmann, or K Boltzmann.
Minus cancels with the 1.
Yeah. Exactly. Log of omega, sum over J, and here we have left only with ones. So this total sum is simply omega. So we have K Boltzmann, 1 over omega, log of omega, and this sum is simply omega. So we are left with K Boltzmann, log of omega. Right? This is exactly what we've seen for the canonical case, microcanonical case. All right? So let us go and see what happens to the canonical situation, right? Okay, so what is Fj?
סטאס, למה 1 חלקי אומגה מתבטל?
We have omega and omega. So this is the sum. The sum over J over all the different states is omega. Right? So all of this equals to omega. Right? Because I sum over all the different states that I have inside my system. Alright, so Fj is 1 over J, 1 over Z, e to the power minus beta, Ej. Okay? So we have D equals to minus K Boltzmann, sum over J, 1 over Z e to the power minus beta Ej. Okay, and here we have log of 1 over Z e to the power minus beta Ej. Okay, great. So what else do we have? So let's separate this guy. Right? So let's separate this guy. So we have minus K Boltzmann, sum over J, e to the power minus beta Ej divided by Z, log of 1 over Z, right? Plus, or minus K Boltzmann, sum over G, 1 over Z e to the power minus beta Ej, and we have to take the log of e to the power minus beta Ej, which is minus beta Ej.
נראה לי חסר מינוס.
Where? Here's the minus.
לא, בחלק הראשון.
Here's the minus. Here's the minus. What else?
לא, כי אם אנחנו לוקחים לאן של משהו חלקי משהו.
But we haven't yet. This is a multiplication. I separated this 1 over Z multiplied by e to the power minus beta Ej, right? In a second, you will see this minus. You will see this minus. You're absolutely right, but I haven't done it yet. Okay, so what we can take out, so we can leave this as it is. So this is, and simply do what you are trying, you suggested. Take this 1 over Z and introduce it as a Z. So we have K Boltzmann, sum over J, Fj, log of Z. Right? And what we have else? We have here plus, we take outside whatever we can, which is beta and K Boltzmann, so it is simply plus 1 over t, okay, plus 1 over t, sum over j, and here we have fj multiplied by ej. And if you go backwards to what we started this class from, this is exactly the entropy of the canonical ensemble that we used previously, without knowing this definition by Shannon. Right? So for the two cases, for the two ensembles that we explored so far, this general definition of Shannon, okay, is good enough. So we accept it as a general definition of entropy for any ensemble, for any system. Okay? And now we have already, or not achieved, but we defined what is the entropy for any system. Okay? So the only thing that matters is you provide me the ensemble, you provide me the different fj's, the different distribution of the probabilities, of the probabilities, and I will give you what's the entropy of the system. Okay? For any ensemble, there's going to be a specific form of this entropy, right? But the general function that is always defines the entropy, it's always like this. S equals minus K Boltzmann, sum over different states of the system, fj log of j. You give me fj and I give you the entropy. Okay. Which is nice, right? Because we know already, we now know what is the microscopical definition of entropy, but it's not good enough. Why it's not good enough? Well, it depends on what you want to do. And remember, I started this lecture by saying we want to go beyond the canonical ensemble, right? We want to develop formalism, which is applicable to different systems, where the canonical ensemble is going to be not applicable or not worth to be applicable. So we want to invert this definition somehow. We want to use this definition of entropy in order to find a way to define the ensembles. Now, how I define ensemble? I define ensemble by saying, well, there are some specific physical conditions. There is a general system, subgeneral system, heat bath, not heat bath, etc., etc. I work really hard, and I eventually obtain those fj's. Right. So now my algorithm is going to be different a little bit. I want to use this general definition of entropy and the knowledge that it has to be maximal. Remember, the entropy at equilibrium is maximal under specific physical conditions. So I'm going to use the following procedure. I'm going to assume, not to assume, I'm going to use this definition of entropy. Okay? And by using this definition of entropy, I will find specific forms of the fj, okay, that satisfy my physical conditions. Okay? So if beforehand I had to explore, I have to expand in Taylor series, I have to assume something about constant temperature, etc., etc., the procedure is going to be the other way around. You're going to state what conditions your ensemble has to satisfy, okay? And based on the principle of maximal entropy, I'm going to define or find what are the different fj's are. Right? I'm not using fj's to find the entropy. I'm using the entropy and the principle of maximal entropy to find the different fj's. Okay? Great. So microcanonical ensemble is simple, but we will, in a couple of minutes, we will show how to define ensembles by using the Shannon definition of entropy. Okay, so we know that this is entropy minus K Boltzmann, a sum over J, Fj log of J. I have no idea what the different Fj's are. Okay? I have absolutely no idea. But I do know, I know S is maximal with respect to Fj's. Okay? This I do know, right? Because we are looking only on the maximum entropy. We know that in any equilibrium situation, the entropy has to be maximal. So I'm looking on all the different Fj's. I'm saying for my given ensemble, right? So my given ensemble, S has to be maximal, and this has to be maximal with respect to what? To the different Fj's. So if there are no constraints, okay, I have a very specific energy, I have a very specific, and it cannot be modified. I do know what this, when this S is maximal, right? This is what Shannon told us. When S is, or the disorder is maximal, is when Fj equals 1 over omega. So with a system where I do not constrain something physical, I'm just saying there is a given energy. What is this energy? I don't know, but there is a specific energy, right? And the system does not exchange energy with anything. I don't observe any constraint that have to be in the system. This principle of looking on the entropy and saying when it's maximal with respect to Fj has to provide this distribution of 1 over omega. So this is the microcanonical ensemble. What happens when I do have constraints?
constraints זה מגבלות, נכון?
Yeah.
אבל מיקרוקולונית לא אנחנו שהיא מערכת מגבלת, זה לא סוג של מגבלה מסוימת?
Not for the EFJs. Right? We haven't assumed anything. Remember, when we, so there is an interesting question. We have assumed something about the system when we looked on the microcanonical ensemble, that the energy was constant. But we had no assumptions regarding the different probabilities. Okay? We had no assumptions. When we don't have any assumptions about the probabilities, S has to be maximal. When it's maximal, when Fj is equals 1 over omega. Okay, but what if we do have constraints? If we add constraints, what happened next? Okay. So the following constraint that I want to add is that sum of j, ej, fj equals u. This is my constraint. There is a given prescribed average energy in the system. Okay, remember, in microcanonical ensemble, the energy could be anything. The only thing that I care that this is going to be a constant energy, but it has no effect on the FJs. Here I'm saying, well, no. Look, all the different FJs and all the different possible energies that the system can have should give me the average energy that I'm prescribing to the system. So this is my constraint. And now I have to find the maximal of S, maximal of my disorder, maximal of my energy with respect to what? With respect to what I'm finding this maxima?
Entropy.
No, I'm finding the maximum of entropy with respect to FJs. Okay? I have to vary all the different FJ that I have in my system, okay, such that, okay, that this guy is going to be maximum.
But if you add the average, so you should get maximum entropy, right? Because
I don't understand the question.
all right, maybe later.
All right. Okay. So what I mean is, it's like in analytical mechanics. There is a maximum principle, but usually we don't look that it's exactly a maximal. We don't care. We only care that the first derivative, or in this case, a first variation, has to be 0. Okay. So we look on our entropy, which is S, minus K Boltzmann, sum over J, Fj, log of Fj, and we say the following thing. Delta S, so the variation of S with respect to all the different Fj's has to be 0. So it's delta of all of this guy has to be equal to 0. Okay, so it's in some sense a critical point. Not a critical point, but the point where, well, the system can have a maxima, it can have a minima. We don't care. We only look on the first variation. So this is the first variation. It basically says that I'm in such a specific state with very specific Fj's, with very specific set of Fj, when I'm linearly changing any possible Fj, okay, the entropy or the value of the entropy is not going to change. Okay. So let's look on what this delta S is equals to. So delta S is delta, or minus K Boltzmann, a sum over J, delta of Fj log of Fj. Right? So it's like taking a derivative, this delta. This delta variation, like you looked see in analytical mechanics, is basically the derivative. Okay? The derivative with respect to the different Fj's. So this is minus K Boltzmann, sum over J. So this is a derivative of a multiplication of Fj and log of Fj. Okay? So what we have over here, so we have log of Fj multiplied by delta Fj plus, okay, plus Fj multiplied by the derivative of Fj with respect to, of log of Fj with respect to Fj is 1 over Fj multiplied by delta Fj. Okay, so delta S equals to minus K Boltzmann stays the same. Sigma of Fj stays the same. Log of Fj is log of Fj. This is delta Fj. This is 1. Fj divided by Fj is 1. Multiplied by Fj, delta Fj. So we can simply say that this is minus K Boltzmann, a sum of log of Fj plus 1 multiplied by delta Fj. Okay. And we say it has to be equals 0. Okay. If there are no constraints. If there are no constraints, it has to equal 0. But we do have a constraint. Right? We do have the constraint. So, but sigma of j ej fj equals 0, equals u. How we solve a problem of finding a minima or a maxima when we have a constraint?
Please don't say Lagrange multipliers.
Lagrange multipliers,
Oh,
right?
great.
Lagrange multipliers. So, but this is very simple, right? Lagrange multipliers. So what Lagrange multipliers says to us is, first of all, we have this constraint. But I forgot, we have another constraint, right? What other constraint do we have in our system? Sum over j, fj equals to 1. It also has to be satisfied. Okay? We cannot simply say, well, all the different fj, we take this fj or that fj. The sum of all the different fj's always has to be exactly 1. Okay? Because the probability to be anywhere has to be 1. So if let's look on the variation of this guy and the variation of this guy. So variation of delta, a sum over j, ej, fj, equals to sum over j, delta, ej, fj. The different energies for the system are not varied. The only thing that is varied is the probabilities of occupying these specific energies. Right? So this simply equals to sum over j, ej, delta, fj. Okay? This is very simple. The variation of this guy. So delta of sum over j, fj, equals to sum over j, delta, fj. This is also very simple. Now we have the variation of entropy, the variation of first constraint, the variation of the second constraint, and then we can use the Lagrange multipliers in order to say, well, to find a maxima of this function s, okay, we need to find a maxima of a function of a variation where we introduce the Lagrange multipliers. So basically we say delta s plus lambda delta of sigma j fj, lambda 1, plus lambda 2 of a sigma over ej fj, all of this equals 0. Okay. So this is the principle of Lagrange multipliers. We look on the system and we introduce the constraint inside the equation that we need to solve. That's it. The variation of the constraint. Very simple. Okay? So now we know delta S is this guy, delta Fj is this guy, and delta Ej Fj is this guy. Okay? So in total we're looking on a system which is minus k of Boltzmann, sum over j, log Fj, plus 1, delta Fj, plus lambda 1, sum over j, delta Fj, plus lambda 2, sum over j, what is Ej, delta Fj. All of this equals 0. We don't know what the multipliers are, lambda 1 and lambda 2. But we see that everything here has multiplication by delta Fj, multiplication by delta Fj, multiplication by delta Fj. So in any case, all of this, okay, has simple multiplication by delta Fj. So we can look on this and say this is minus k Boltzmann, sum over j, and inside we have log of j plus 1 minus lambda 1 divided by k Boltzmann, okay, minus lambda 2 divided by k Boltzmann, okay, multiplied by Ej, and all of this multiplied by delta Fj. Now lambda 1 is constant, lambda 2 is constant, so I would like to rewrite all of this in terms of new constants. It doesn't matter. So I have minus k Boltzmann sum of j, log of fj, plus 1, plus lambda 1 tilde, plus lambda 2 tilde, ej, delta fj, all of this equals 0. Now, the modifications that I introduced in all the different delta fj's are independent, completely independent of each other. So in order for this sum to be 0, since all the delta fj's are independent, all the different summands has to be equal 0. Why? Because delta fj's are absolutely independent. Okay, so what we look on log of fj plus 1 plus lambda 1 tilde plus lambda 2 tilde ej equals 0. Okay, so we basically say that log of fj equals minus 1 minus lambda 1 tilde minus lambda 2 tilde ej, and fj equals to e to the power minus 1 plus lambda 1 tilde multiplied by e to the power minus lambda 2 tilde ej. This is very good. Why it's very good? Because in canonical ensemble we know that fj equals to 1 over z e to the power minus beta ej. So we are almost there, right? We started with something very general. We said, well, we have only this constraint that the energy, average energy, is equals to U, right? And immediately, only by using this constraint, we obtain that this general form of FJs are exactly as the general form for the canonical ensemble. We still haven't, I haven't showed you how to obtain this. This is beta and that this is Z, okay? But I will show it to you next week, hopefully. Yeah. So we haven't finished, but this is the way that we can build new ensembles. I have this definition of entropy. I define that I need to find a maximal of this function with respect to all the different FJs. I use constraints, and out of thin air, those distribution or those probabilities appear. We will see how it works for exactly finish this for the canonical ensemble, and we will see how we define grand canonical ensemble by using this method. Good luck with the quiz next week.